LeChatelier's principle again. Yesterday we talked about adding stuff in, taking stuff out. We talked about changes in temperature and things like that. Today we're going to talk about changes in pressure and volume and how that affects it. And really they're kind of linked together here, so we're going to talk about that. If you compress a container, so if you take a container and, for example, it's a cylinder or something, you compress it, okay, the volume gets smaller. So I need you to remember that. If you compress it, the volume gets smaller. What happens if the volume gets smaller? As far as concentration goes, what happens? Concentration goes up, yes? Because you now have a smaller volume, a smaller number on the bottom, the concentration is going to go up. Vice versa, if you make the volume larger, the concentration goes down, okay? So you have to remember that when we're talking about pressure and volume here. Compressing a container decreases the volume, causes an increase in system's total gas pressure. The expansion, increasing the volume, causes a decrease in the total gas pressure. So that's part of it. The other part is this. The system's response is based on the total amount, or the total moles, of gaseous reactants compared to the gaseous products. So we're talking about the amount of gas reactants versus amount of gas products. That's also going to factor into this. So not only the volume change, but also that. If you increase pressure, so I take this cylinder and I increase the pressure, the reaction that is favored is the one that will give you the least number of molecules. All right? So it's going to be the least number of moles, basically, is the one that will be favored, the fewer gas molecules. If I that's an increase in pressure. If I decrease the pressure, in other words, if I make the container larger, I decrease the pressure, then it favors the one that fills it up more, which is the more number of gas molecules. Okay, so it favors the reaction with more gas molecules. All right, we're going to take a look at that with these charts here right away. So here we go. My subscripts didn't turn out very well, but that's okay. Here we go. This is 1 mole here. This is 2 moles here, right? So you can think of it in terms of moles. If you want to think about it in terms of Avogadro's number, sure, go ahead, whatever. But basically, you don't even have to think about that. 1 molecule all joined together, or basically that would form 2 molecules of NO2 gas here. So for every one of these, I get 2 over here. If you apply pressure to this system, it will favor the reactants. Because if you apply pressure, you're squeezing down the volume, it compresses it, it favors the reaction that produces less gas molecules, right? So 1 versus 2, this one would be favored if I compress the system. If I enlarge the system, then it would be this one that would be favored, because now I'm trying to fill up that container with more gas molecules, okay? So when we look at our charts here, we're going to do the following, and this is the key here. All right? So if we compress N2O4, I said we would favor the least number of gas molecules, right? So if I compress this, it's going to favor the 1 versus the 2. This is going to be favored, N2O4. However, before we start, if I compress the system, what happens to the concentration initially? It goes up, right? So we need to show that. So it's going to start here and it's going to spike up. And so is this one, because both concentrations are going to get larger, yes? Okay, so that's how it's a little bit different than last day. And then I said it would favor the N2O4 because there's only 1 gas molecule being formed there compared to, there's only 1 N2O4 compared to 2 NO2s. So N2O4 is going to get made more until it gets to its equilibrium here. And we're going to use up the NO2 until it reaches equilibrium there. Okay? So a little bit different, because you do get this initial spike in concentration here due to the fact that we are compressing it, we're making the volume smaller. Concentration goes up. Okay? What vice versa, of course, what happens if I expand the system? You know, I expand the system. Volume gets larger. If the volume gets larger, the concentration gets weaker. So you're going to see a spike down and a spike down. If I expand the system, I'm giving it more room. It favors the one that goes to more molecules, which in this case, if you remember back to this equation here, the more molecules one is now this one here. The forwards reaction is favored now, and I would get more NO2 and less N2O4. I'd be using up the N2O4. So more NO2 in this case. So more NO2, so that would look like this until they reach equilibrium somewhere over here. And I would be using up that N2O4 to get to there. Okay, so that would be the reaction in that case there. And once again, this one would favor the forwards reaction. Okay, favors the forwards reaction for that one. And for the one before this one, we would favor the reactants. Okay, or favor the reverse reaction. I'll just write that down there. Favors reverse reaction or favors the reactants. So if I compress it, it favors the reactants. If I expand it, it favors the products. Okay? What you have to remember is there is that always that spike in concentration. Well, almost always, I should say. Well, there usually is. But there's going to be a spike in concentration. They both are going to go up. They might both go down because remember, it affects both gases. But then what happens after that is it tries to get back to equilibrium, of course. All right? Now, pressure volume changes do not change a value in the Kc. So once again, Kc values are not affected by pressure volume changes. So maybe this happens though. What happens if I have the same number on both sides? In other words, if I have the same number of molecules on the left-hand side as the right-hand side. If you look at this particular equation here, look, I got one of these and one of these gives me two of these. Well, how many molecules do I have on the left-hand side altogether? Well, I have two, right? I have one H2 molecule and an I2 molecule, so I have two molecules on the left-hand side, and it turns out I get two HIs on the right-hand side, so those are the same number on both sides. What happens then? Well, there is no equilibrium shift because I'm not making, we have the same number, so I could do any kind of stress I want to this. I could increase pressure, decrease pressure, it's not going to shift. However, what does that look like when we go to graph that? And the answer is, well, when I go to graph this, what's going to happen to the H2, I2, and HI concentration? I'm expanding the system. So what happens if I increase the volume? If I expand the system, what happens to the concentration of these three? Goes down. So that's where we're going to start here. This one's going to go down. This one's going to go down. And this one's going to go down. Okay? Now mine, of course, unfortunately got kind of cut off here, but that's okay. Then, does it need to shift equilibrium here? No, because it doesn't matter. I got the same number of molecules on both sides. So I'm not going to have it increasing, or I'm not going to have one decreasing. They're basically just going to stay the same. The concentration is going to go down for those, and that's it. Okay? Nothing else happens. So then you're just going to draw a straight line across here like this. Straight line. And straight line. And in fact, I know that you guys down here have this shifting non-equilibrium. You guys can actually just probably scratch that out and keep going all the way over to equilibrium here again. I'll call that my equilibrium there. It's just going to remain consistent. There is no shifting equilibrium with this. There is no trying to favor the reactants or products. It is just what it is. That's it. It's done. Okay? So usually we just kind of cross that out and just keep going, and eventually, once again, it's still going to be at equilibrium. All we did was just decrease the concentration. That's all, the only thing we did. All right? Good for that one? Same thing would happen if we compressed the system, by the way, except the only difference is the concentration would have spiked up for each one of these three, and then we would have been done again. Okay? So that happens when the reactants and the products have the same number of molecules on both sides. Okay? If you add an inert gas, so if you just added some kind of helium or neon or something like that into this system, it's not going to react with anything. So adding an inert gas increases the total pressure of the system for sure. It increases the total pressure, but it doesn't change the concentration of any of those gases, okay? And it doesn't change the equilibrium. It doesn't shift it any which way or anything like that. So it does not affect the partial pressure of the individual reactant or product of gases. There's no equilibrium shift, so you would see the same kind of thing. Catalysts can be used to speed up or slow down the reaction rate at which equilibrium is established, but they will not affect the final equilibrium position. So they might speed it up. You might get to equilibrium faster, but once you get to equilibrium, it's going to be the same as it was before, okay? Kc remains constant for all these things, catalyst or not. And the main thing here, of course, that we have to remember, because there's always a question on something about this, is that the only thing that affects Kc, the only thing that affects that number is, in fact, temperature change, okay? A change in temperature. So Kc is only affected by temperature change, all right? And basically, that's it for today. I'll give you guys a few questions here for practice, and we're good to go.